overview of how data traverses our systems. We're also not describing the OSI protocol suite. Indeed, most of the protocols we use today are based on TCP/IP, but the OSI model is one that we can apply to many different protocols, and it works perfectly with the TCP/IP protocols that we use today. Also keep in mind that there are many different protocols that might operate at an individual layer of the OSI model. So as we step through an individual layer, keep in mind there might be tens or even hundreds of protocols that might exist and work at that particular layer. By understanding this OSI model, we can converse with other people in information technologies in a way that we would all understand. It doesn't matter if they're working inside of your own company or with a different organization. When you mention OSI Layer 7 or OSI Layer 4, everyone understands what that means and what effect it has on the overall operation of the network. If we start at the top of the OSI layer or OSI Layer 7 and work our way down to OSI Layer 1, we have Layer 7 being the application layer. Layer 6 is the presentation layer. Layer 5 is the session layer. Layer 4 is transport. Layer 3 is network. Layer 2 is the data link layer. And Layer 1 is the physical layer. There are many different mnemonics that people use to memorize this, but if you start at the top and work your way down, you can take the first letter of each one of these layers, and you might have a term such as, all people seem to need data processing. That's application, presentation, session, transport, network, data link, and physical. Let's start our conversation of the OSI model at the bottom of the OSI model, or Layer 1. We refer to this as the physical layer because it's describing the physical signals that we send through the cable and fibers on our network. At this layer, we really don't have many protocols to speak of because we're really just talking about getting a signal from one part of the network to another. When we refer to a physical layer problem with the network, we are referring to the OSI Layer 1 physical layer. This means that we might have a bad cable, a bad fiber, there might be interference on a wireless network, and it may require us to do a series of tests to determine if we are really able to get a signal across this particular wire or this particular fiber so that we can keep this network running. A lot of the troubleshooting that you do at Layer 1 is running loopback tests, testing cables and fibers, and checking different adapter cards and other devices to make sure they're working properly on the network. One step up from the physical layer is Layer 2, the data link layer. This is the fundamental layer that's used to communicate between two devices on the network. We often refer to this as the MAC address layer because that is the data link control layer, or DLC layer, that is commonly associated with the network cards that are in our devices. And most of the time, these are Ethernet adapters or wireless adapters, and we refer to that physical address on that device as the data link control address, or the MAC address. In this case, MAC address is not referring to an operating system, it's referring to the media access control address. So anytime you hear someone talk about a MAC address, they are referring to the hardware address of that particular adapter card. Since the network switches that we use on our network determine how to forward traffic based on the destination MAC address, this is a layer that we often refer to as the switching layer. So anytime we're referring to a MAC address, a problem with a switch being able to operate, or anything else that may be associated with this particular hardware address, we're referring to OSI Layer 2, the data link layer. The next layer up is OSI Layer 3, or the network layer. We often refer to this as the routing layer because this is the layer that routers use to determine how to forward traffic. And they are specifically looking at the destination IP address in order to determine what the next hop might be for traffic traversing the network. This is also the layer that we're able to fragment these frames into multiple pieces, especially if we're sending it across a network that may require smaller frames than what is on our local network. So we can cut those frames up into smaller pieces to be able to fit them through the network and then put those pieces back together on the other side. Anytime we're referring to a problem relating to IP addressing, subnet masks, anything related to an IP address or anything about routing, then we're probably referring to Layer 3, the network layer. Layer 4 is the transport layer, and as the name implies, we're referring to the ability to transport information from one device to another. You might also refer to this as the post office layer because this is responsible for getting your letter or your information from one side of the network to the other. The protocols that are often used and operate at layer 4 of the OSI model is TCP, that stands for Transmission Control Protocol, and UDP, or User Datagram Protocol. These two protocols are commonly responsible for getting all of the information within our IP packets from one device to the other. In many cases, this involves taking a large amount of data, putting it into smaller pieces to be able to get it across the network, and then putting those pieces back together on the other side. Before we can send that information from one side of the network to the other, we may need to create a session so that a device is able to receive that data. Layer 5 is the session layer, and it provides communication management between point A and point B. Anything relating to the initiation of a session, stopping the session, or restarting the session can commonly be associated with that Layer 5 session layer communication. If an application is using some type of control protocol or you're tunneling information within existing data, then you're probably using OSI Layer 5. OSI Layer 6 is responsible for putting all of this data into a format that we will eventually see with our human eyes. This refers to character encoding, application encryption, and decryption, and it's often combined and discussed in conjunction with the application layer at Layer 7. Layer 6, or the presentation layer, is the layer that is commonly in operation just prior to us seeing this data on our screen. And the top layer of the OSI model is OSI Layer 7, or the application layer. This is the layer that we see on our screen. So anytime that we are interacting with an application, we are operating at Layer 7 of the OSI model. Common applications that would operate at OSI Layer 7 are HTTP and HTTPS, FTP, DNS, POP3, and thousands of other application protocols. Well, that's a broad overview of the OSI model, but how do we fit things in the real world into each of those layers? Let's start down at the bottom with Layer 1, or the physical layer. When we refer to cables, fiber optic connections, the signal going across those connections, or a wireless network, then we're operating at OSI Layer 1, or the physical layer. When we refer to OSI Layer 2, or the data link layer, then we're talking about Ethernet frames, MAC addresses, or addresses referred to as Extended Unique Identifiers, or EUI. There are EUI 48 addresses and EUI 64 addresses, for example. And as we described earlier, anytime we're referring to the switching process, we are referring to OSI Layer 2. At OSI Layer 3, or the network layer, we're referring to IP addresses. So anything that has an IP address or subnet mask, or referring to the way that routers forward traffic, all happen at OSI Layer 3. If you're referring to a TCP port or a UDP port, then we're operating at OSI Layer 4, which is the transport layer. At OSI Layer 5, or the session layer, we're using control protocols to start and end different sessions, or we may be tunneling traffic using protocols that operate at OSI Layer 5. We often associate the encryption of application data with OSI Layer 6, or the presentation layer. So if you're communicating to a website and you're using SSL or TLS to be able to encrypt and decrypt that data, that process is occurring at OSI Layer 6. And at OSI Layer 7, or the application layer, is where you are interacting with the application itself. Anything that you're seeing on the screen, the application itself, or any messages from the application are often referred to as Layer 7 information. If you wanted to drill down a little bit further into the OSI model, you might want to capture some data on your network and view that data inside of an application such as Wireshark. I have a Wireshark protocol decode on my screen where I've captured data on my network, and this Wireshark has 3 separate windows that is displaying different views of the same data. The top window is a frame-by-frame breakdown. For example, I have highlighted frame 88 on this top window. The middle window describes more detail of what different information is contained within that single frame. And on the bottom window, we have a hexadecimal and ASCII breakdown of the data itself. Let's focus our view on this middle window, which is a summary of this highlighted frame 88. You can see that there are 5 different lines of data inside of this single frame where the protocol decode has separated out the individual protocols within the single Ethernet frame. Let's start with the one at the very top, which describes frame 88, which has 2005 bytes on the wire and 2005 bytes were captured by Wireshark. If you wanted to associate that line with the OSI model, that would be best associated with layer 1 or the physical model. Next down is Ethernet 2, which has a source MAC address and a destination MAC address. And since we are describing MAC addresses, everything within that line of the Wireshark decode is associated with layer 2 of the OSI model, or the data link layer. The next line down describes the Internet Protocol, or IP. And as we described before, IP fits squarely in layer 3 of the OSI model, or the network layer. And in fact, there are individual IP addresses listed here for the source IP address and the destination IP address. And you can see there is a DNS resolution here that shows that the IP address of 72.14.247.19 is also associated with googlemail.l.google.com. As we move down this list, we're moving up the layers of the OSI model, and the next one is the Transmission Control Protocol, which means we're communicating via TCP for this Google Mail communication. Since TCP is in this list, we must be at OSI layer 4 or the transport layer, and indeed you can see TCP port numbers for the source and the destination of this traffic. Since the destination port is port 443, Wireshark has already filled in that we're communicating over an encrypted channel using HTTPS. And if we go one layer down into the secure socket layer, this effectively encapsulates the top 3 layers of the OSI model. So secure socket layer and everything underneath it are referring to layer 5, the session layer, layer 6, presentation layer, and layer 7, the application layer. Here's a summary of that protocol decode broken out into the different layers of the OSI model. We had electrical signals at the physical layer. Layer 2 at the data link layer had Ethernet frame information. Our IP addresses were at layer 3 or the network layer. Our TCP encapsulation with our TCP port numbers is at the transport layer. Our session layer linked the presentation information to the transport. Presentation layer was obviously performing that SSL or TLS encryption and decryption. And layer 7 or the application layer is referring to that Google Mail front end and being able to send and receive emails using mail.google.com. Hopefully you're now able to see how this very broad description of an OSI model can be applied to practically any communication that's occurring over the network. And this allows us to talk with other IT professionals and communicate in a way where everyone understands exactly what we're referring to when we talk about a layer 1 physical problem or a layer 7 application problem. If you were to walk through a data center, you will see many of these racks all together with a lot of different equipment installed in each one of them. All of these devices work together to be able to take data from one part of the network and move it to another part of the network. Each of these devices is installed for a specific reason, and it's helpful if we understand why we installed that particular piece of equipment to begin with. Over time, we may be installing more of this existing equipment into our racks, or we may be installing new technology. So in this video, we'll look at different types of devices and how we might use them in our data center. Let's start with one of the most common devices that you'll find, which is a router. A router allows us to take data on one IP subnet and route that information to a different IP subnet. These may be subnets that are next to each other in the same data center, or these IP subnets may be located in different parts of the world. We refer to a router as an OSI Layer 3 device. At the OSI Layer 3 or network layer, we're referring to IP addresses, and IP addresses is exactly what's used by a router to be able to determine the next hop for this information. You may sometimes see this routing functionality also included inside of an existing switch, and we often refer to these as Layer 3 switches, which of course is referring to that OSI Layer 3 functionality. It's not that the switch itself is now operating at a different OSI layer, it's just within that same piece of equipment, we have both a Layer 2 switch and a Layer 3 router, so we've abbreviated that as a Layer 3 switch. These routers often connect many different types of networks. So we may be connecting a local area network or a LAN to a wide area network or a WAN. These might also be copper-based connections or fiber-based connections. So we may have routers with many different connections or interfaces on them, and we're connecting many different diverse networks to all of those different interfaces. Another common device is a network switch. Switches operate at the MAC address layer to be able to forward traffic, so we'll often refer to that as an OSI Layer 2 or data link device. These operate mostly in hardware. The hardware inside of these devices is referred to as an ASIC, that is an application-specific integrated circuit. There are many different functions and capabilities inside of these switches, especially if you're using one designed for the enterprise. For example, many of these switches have the ability to include power on the same wires as your Ethernet connection, and we refer to that as Power over Ethernet or PoE. And as we mentioned before, you may hear folks refer to this as a Layer 3 switch if the switch includes some type of routing functionality built into the device itself. Security on our networks is also important. That's why you probably are using a firewall at home, and you most certainly have a firewall in your office. A traditional firewall allows you to filter traffic based on a TCP or UDP port number. But if you have a more modern firewall, you're probably using a next generation firewall or NGFW, which is able to identify applications traversing your network and allow you to manage whether that application should be allowed or not allowed on your network. Most firewalls also have additional functionality. For example, it's common to find firewalls that will allow us to encrypt traffic traversing the network through a virtual private network or VPN. It's very common to have a firewall at one remote site and a firewall at another remote site and be able to create an encrypted tunnel between those firewalls using this VPN functionality. And most firewalls can also operate as a Layer 3 device, which means the firewalls themselves can act as a router. That's because they are often sitting right between the ingress and egress point of your network, where all the traffic on the inside of your network is going to the outside or internet connection, and your internet traffic is coming inbound to your local network. We rely on the firewall to be able to manage the communication between the inside and the outside of the network. To be able to perform this functionality, many firewalls also provide network address translation or NAT, and because they are a router, it's very common to have dynamic routing protocols supported inside of the firewall as well. Many data centers might also have standalone IDS or IPS devices, although much of that functionality is also integrated into the more modern next-generation firewall. IDS refers to an intrusion detection system, and the IPS refers to an intrusion prevention system. Both of these work in similar ways. They're looking for attacks that are inbound to your network and are able to identify, alert, and in many cases prevent that attack from gaining access to your network. These are commonly known attack types. These might be exploits against operating systems or the applications that you're using, and they might take advantage of known vulnerabilities with those applications or systems by taking advantage of a buffer overflow, a cross-site scripting vulnerability, or other known vulnerabilities to those systems. If you're using an intrusion detection system, it's able to alarm or alert if it ever sees any of these inbound attacks. If you're using an intrusion prevention system, it's able to go a step further and block that particular attack before it gets inside of your network. Since an intrusion detection system is not able to block that traffic, it's very common to see an intrusion prevention system used on our enterprise networks. If you've ever used a website that may be accessed by millions of people every day, you may be wondering how that site is able to remain up and running without any type of downtime. In most cases, it's because that site is using a load balancer to be able to distribute that load across multiple physical servers. As the end user, you may have no idea that this load balancing is taking place, but if you were to look at the data center for this organization, you might find a large number of web servers or database servers in farms that can be used in conjunction with this load balancer to maintain uptime and availability. These load balancers are also very good at identifying any outages to these servers. So if one of the servers happens to fail due to a hardware error or some type of software problem, the load balancer can recognize the issue, take that server out of the rotation, and continue to provide access to these services using the remaining devices that are connected to the load balancer. Here's a common design for a load balancer where users on the internet would be accessing a service at a location. To the end user's perspective, they're accessing a single server, but they're really accessing a load balancer that is distributing that load between multiple servers inside of that company's data center. These load balancers can also optimize the communication. For example, it may perform TCP offloading so that the communication to all of these servers on the inside of the network are occurring as quickly as possible. These load balancers can also act as an SSL offload, which means that they will provide the encryption and decryption capabilities instead of having the servers themselves manage that process. Data might also be cached on the load balancer, so requests made to the load balancer can be answered immediately instead of going all the way down to the server to provide that data. And load balancers are also very good at prioritizing different types of traffic over others. There might be certain web pages that have higher access than others, and you can commonly perform that prioritization using quality of service or QoS. Load balancers can also provide application-centric load balancing, where certain pages may be located on certain servers, and all of the requests to those pages would go exclusively to those individual servers. Many organizations have security concerns about individual users being able to directly communicate with a server or service that's on the internet. One of the ways that the organization can manage these connections is by putting a device in the middle of this conversation called a proxy. This proxy is responsible for taking the user's request, performing that request on their behalf, receiving the answer to that request, verifying that the answer doesn't contain some type of malicious software or malicious code, and then providing that answer to the end user. That is the purpose of a proxy, to sit in the middle of the communication and make that communication on the user's behalf. Since the proxy is sitting in the middle of the conversation, it's a perfect place to do caching. So the user can make a request to a web server. If that request has already been cached by the proxy server, the answer can go right back to the user without having to access the internet. We might also provide access control from the proxy server so that we can request a username and password from the user in order to gain access to the internet. From that point, we might want to filter URLs or perform some type of content scanning to make sure that the user is not receiving any type of malicious software. Some proxies require you to configure the operating system or the applications that you're using to identify the proxy and be able to use that to send and receive communication. But not all proxies work in that explicit manner. There are also transparent proxies that will work invisibly without making any changes to the operating system or the applications in use. It's very common to store documents and other files on centralized storage facilities inside of our data centers. One type of storage is referred to as a network attached storage, or NAS. We often refer to this network attached storage as providing file level access. That means that if we wanted to gain access to information within a file, we need to pull the entire file across the network into the memory of our system. And when we're writing information or changing information in that file, we will need to write the entire file back to the NAS. A more efficient way of communication might be through the use of a storage area network, or a SAN. This is very similar to reading and writing information from a local storage drive, where instead of copying the entire file to be able to change just a bit of information within it, we have block level access, which means that we can change just the blocks that have been modified. And when you have very large files, this can be a very efficient way to modify just a little bit of information within that very large document. Whether you're using a NAS or a SAN, you're probably transferring a lot of files to these systems. And for that reason, we want to be sure that we're using the most efficient method of communication. It's very common, for example, to put the NAS or the SAN on its own isolated network, and it's commonly a network that has very high bandwidths. If you're in your office and you look at the ceiling, you might see a device like this. This is an access point. This device allows us to communicate wirelessly from our device to the rest of the network. This is not the wireless router that you might be using at home, which is a router and a wireless access point and a switch in the same device. When you're in larger enterprise environments, you're usually using a device that is purpose-built for a single function, and having an access point means that we're using this for wireless communication and wireless communication only. On the other side of this wireless access point is very commonly an Ethernet connection. So this is bridging communication between the wireless network and the wired Ethernet network. That's why we refer to access points as an OSI Layer 2 device, or a data link layer device, because it's making that translation between the 802.11 wireless network and the 802.3 Ethernet network. In most businesses of any size, you probably have more than one access point. That's because you probably have a very large building or series of buildings, and you need to be sure that everyone is able to access that wireless network wherever they happen to be inside of these buildings. But this means that we have to manage many different wireless access points wherever they might be in our local network or in a remote site network. And we might need to manage security settings, access policies, and other configuration parameters within that access point. We also have users that may be very mobile and moving between different parts of the building or moving from one building to the other, and we need to make sure that they can seamlessly roam from one access point to the other so that they are always connected to the network. Instead of connecting to each individual access point to make these configuration changes or manage this process, we can have a centralized management tool that allows us to manage all of our access points from one central place. This is a wireless LAN controller, and it gives us that single pane of glass so that we can manage the entire infrastructure while we're sitting in one chair. From this single device, we can deploy new access points with a full configuration. We might want to set up performance or security monitoring and be alerted if we happen to see anything across any of our access points. We can also take any changes that we need to make and deploy those automatically to all of our access points with one click of the mouse. This also allows us very commonly to create reports on how much our access points are being used and be able to understand if we need to update or change any of our access point locations. These are often proprietary systems, so if we have an access point from one particular manufacturer, then we're also using the wireless LAN controller that is also from that same manufacturer. If you were to somehow somehow get inside of the networking cable and see what was going back and forth over that connection, you would see there was a lot of different activity going on across many, many different systems. All of these are designed to focus on specific functions. For example, we may need to get a piece of data from our network to a network that is on another part of the world. Or we might need to access a system that is already located somewhere else and provide technical support or be able to share a screen. There's also a need to have traffic management on our network so that certain applications have a higher priority than other applications. And lastly, we need to be sure that all of our systems are up and available, and it may take specialized protocols to make sure that that occurs every step along the way. One way to speed up the process of getting access to data is through the use of a CDN. This is a content delivery network. And as the name implies, it is designed to provide a way to get data very efficiently from one central point to an end user. These are often set up in geographical areas. So there might be a CDN server in North America, South America, Africa, Asia, other parts of the world, and you're able to cache information at each one of these points. It takes time to get data sent from one part of the world to the other. So if you can have all of your North America users access the North American CDN, it's much faster than having them all go out to a centralized server that might be located in Europe. So if you're watching this video on YouTube or on the Professor Messer website, you're using a CDN right now. It's a way for very small or very large sites to be able to distribute their data to users all over the world and make sure that that data is as accessible and efficient as possible. For those of you that work outside of your corporate facility or perhaps do a lot of work from home, then you're probably already familiar with a virtual private network or a VPN. This allows you to connect to a remote network while sending all of this data encrypted across the network. It's a very secure way to transfer data, even across networks that would be inherently insecure, such as the public internet. VPNs often use a device called a concentrator or a head-end device to be the central connection point for all of the users who are accessing that VPN. This is often a purpose-built appliance that's designed to do high-speed encryption and decryption of network data in real time so that you can have many people being able to send secure data across the network, decrypt all of that data, send it to the inside of the network, and then reverse that process to get the response back to the user. This can be a standalone device, but very commonly we integrate this VPN concentrator function within a next-generation firewall itself. Because of the encryption and decryption process required to perform this VPN concentration, we usually will use a purpose-built appliance or piece of hardware to be able to do this. That provides very high throughput and can support hundreds or even thousands of users simultaneously. But if you have a smaller network, you may not need a purpose-built appliance, and there are many VPN concentrators that will run as software on an existing operating system. You may have to install a specialized piece of software to be able to use a manufacturer's VPN, although there is VPN software that does ship with Windows, Mac OS, and Linux operating systems so that you can connect to many different kinds of VPNs using that generic software. Not all applications are designed to run simultaneously on a network, and certainly some applications may have a higher priority to your organization than other applications. For example, there might be a real-time audio or video stream that has a higher priority than a file transfer. Because of these requirements, it's very common for network administrators to provide some type of prioritization to these applications. This is often done through a quality of service or QoS configuration. You might also refer to this as traffic shaping or packet shaping. This allows the administrator to control what type of applications can flow through their network, usually based on bandwidth usage or particular data rates. This might allow your real-time applications to have full control or access to the network and put a lower priority on other applications that may simply be transferring files. To control this quality of service, you may need to make configuration changes inside of a firewall, a router, or a switch. These devices might have a pre-built list of applications and might also allow you to add your own applications to the list. And at that point, you can decide what priority the applications might have relative to everything else that's running on the network. One of the challenges we often run into with technology is that it's very good at performing a task. And often it can perform these tasks over and over and over again without any type of human intervention. Unfortunately, this could also put a device into a state where it's performing the task over and over and over again and never finds a way to complete or end that particular task. For that reason, we've often built in different functions with our protocols so that we can recognize when a task may be going on too long and simply remove that task from the network. One common way to provide this identification is through the use of a time to live, or TTL. A time to live is effectively some type of timer. This timer may be based on the time of day, or it may be based on the number of iterations that a particular task completes. Once that timer hits 0, we can then have that task stop what it's doing, or we can drop that task from the network. There are many different cases for a time to live. One is a packet that is constantly looping between different routers. We might want to have that packet automatically dropped if that loop occurs a certain number of times. Another good example of a time to live might be to clear a cache, where we might access a website, have that website stored in a cache, and then that cache is only available for the next 60 seconds or number of minutes. When that timer hits 0, the cache is cleared, and the next time that website is accessed, you would have to go all the way out to the site to be able to bring that information back, at which point that is placed in the cache and another timer starts. Another example of using a time to live to stop traffic that is looping around your network is through the use of a routing loop. This is a really good example of where you might have router A thinks the next hop is router B, and router B thinks the next hop is router A. And what you'll find is that the packet goes back and forth between those routers over and over and over again. If you were going to perform a trace route, you would see this loop in the trace route itself, where the route goes to 10.1.10.1, then it goes to 10.2.10.2, then back to 10.1.10.1, then back to 10.2.10.2, and so on. And this will continue all the way through until it reaches a time to live. This is something that does occur occasionally because you might have many different routers, and those routers have many different routes. So it's very easy to make one single IP address mistake in a static route and create this routing loop on your network. For routing loops, we use a TTL field inside of the IP packet itself. This allows us to identify and stop a loop automatically if one occurs. In this example, we have router 1, and router 1's next hop is router 2. We've configured router 2 with a next hop of router 1, which means that this packet is going to go back and forth between these routers until something stops that loop from occurring. Fortunately, we built functions within IP, or the Internet Protocol, to look for this loop to occur and stop it if it finds that it's occurring over and over again. In IP, the time to live is referring to the number of hops that a packet will go through a router. Each time a router processes a packet, it decreases the time to live by 1. And when that value gets down to 0, it discards the packet, effectively ending the loop. The default time to live for Mac OS and Linux is usually 64 hops, and the default time to live for Windows is 128 hops. Since the router is decreasing the time to live by 1 each time the packet goes through, it's watching that number decrease every time it goes through a looped connection. And when the time to live gets to 0, the router drops that particular packet. If we were to look at the frame of IP, you can see there's version numbers, header length, type of service, total length, and other fields within the IPv4 header. The one we're interested in is the one called time to live, and that's the one that the router will use to determine if it's gotten down to 0 and if it should discard this packet from the network. Here's a very simple protocol decode of an IP header. You can see this is frame 1. We have the Ethernet information, what the MAC address is for the source MAC address and the destination MAC address, and this is an IP version 4 header. You can see the source IP address and the destination IP address in the header itself. If we were to break this header open and look at those individual fields that we mentioned from that previous slide, you can see there is a differentiated services field, a total length field, an identification field, and right here is a time to live field. The time to live for this particular packet is 58 hops. So this packet would need to go through 58 more routers until this got down to 0, at which point it would be removed from the network. In most cases, our total number of hops between us and the destination that we're trying to visit somewhere on the internet is usually around 12 to 16 hops, sometimes more and sometimes less. But that's a relatively small number when you consider that the total default time to live on macOS or Linux is 64 hops, and the default on Windows is 128 hops. That gives us plenty of room to be able to get data from one side of the internet to the other and not have that information accidentally dropped by a router. Depending on the protocol you're using, time to live may have a different definition. With routers, time to live is associated with the number of hops, but in DNS or the domain name system, the time to live is associated with the total number of seconds. Let's take a scenario where we're performing a DNS lookup, and you can do this yourself by using NSLookup or dig, and you can resolve or look for the device www.professormesser.com. And your DNS server will return some type of IP address associated with the Professor Messer web server. Inside of that DNS resolution is information about time to live. This tells us how long we should cache this local entry on our system. So if we want to cache it for a certain number of seconds. How many seconds? Well, we're going to cache it for the time to live seconds. The time to live is included with the configuration on a DNS server, and this is the output from the command dig www.professormesser.com. You can see that the answer section, where the DNS server is providing us information, says that the server www.professormesser.com has a time to live of 300. This is an internet address. The A is for address. And then we have 3 different IP addresses associated with my web server. This 300 value is the one telling our local machine, keep this IP address in your cache for 300 seconds. If you do the math, that is 5 minutes. Once that 5 minutes has elapsed, our local cache removes that particular resolution. And if you want to know the IP address for that same server, you would need to perform another DNS query to update your cache for another 5 minutes. This allows me, as the administrator of my web server, to be able to change the IP address in my DNS configuration, and I can feel relatively secure that most people will have an updated version of that IP address within 5 minutes. We use time to live for many other protocols as well, so make sure you look at the documentation for that protocol to understand exactly how we're measuring time to live for that particular protocol. Cloud computing Has undeniably changed the way we approach technology. With one click of a button, we can deploy an application and multiple services, all seemingly with unlimited resources. We're able to scale up and scale down these applications as we need, providing elasticity, especially in times when we have large demand, and then scale it back down when that demand goes away. We also have applications that we can now scale up or scale down and access those applications from anywhere in the world. Cloud computing also uses multi-tenancy, where many different customers are using the same cloud infrastructure. This allows for efficiency in the use of technology and efficiency in how much it costs to use this technology. Not only do we have virtual servers that can live in that cloud computing infrastructure, we can also have virtual networks. Let's take the scenario where we might have 100 individual servers that are running in our data center. That's a relatively large farm of servers. We've designed this infrastructure to have redundancy in the network. There are multiple servers. We've got load balancers and multiple firewalls, and we've designed it for uptime and availability. But now let's take this entire physical infrastructure and let's move this infrastructure to the cloud. We're going to migrate 100 physical servers to effectively one very large physical server. Inside that one very large physical server, we will run 100 virtual servers inside of it. Now that we've taken these 100 physical servers and migrated them to a cloud infrastructure, what do we do with our networking infrastructure? Not surprisingly, we will virtualize this network infrastructure as well. This is referred to as Network Function Virtualization, or NFV, where we can replace our routers and our switches and our other networking devices with virtual versions of those networking devices that are running in this virtualized environment. Although our firewall and our switches and our routers are no longer physical, they still have the same functionality. We can see those devices, our network interfaces, and everything about the network configuration all from our hypervisor. So we have the same functionality, it's just now in a virtual appliance. Just as we're able to push a button and deploy a new server, we can push a button and deploy a new firewall or a new switch or make a router configuration all within this virtualized world. This gives us a lot of flexibility for deploying applications, designing the network connectivity for those applications, and connecting our different cloud infrastructures wherever they might be in the world. A common application instance inside of a cloud infrastructure might include a web server, a database server. There could be load balancers, virtual switches and routers, and virtual firewalls. All of these will run inside of a virtual private cloud, or a VPC. It's very common, especially in larger environments, that you would have separate VPCs for different application instances or different parts of the company. This allows you to keep all of these systems separated, but still allow you to manage all of them as individual virtual appliances. Although these VPCs may be different application instances, we might still want to have devices within those separate VPCs be able to communicate with each other. To provide that communication, we need a device in the middle called a transit gateway to be able to connect all of these VPCs together. You can think of this transit gateway as a cloud router that allows us to connect and allow communication between all of our different VPCs. If you need connectivity to these VPCs from the outside, you may need to add additional security in the form of a VPN connection. This allows someone who may be at a remote site to be able to bring up a VPN tunnel, connect to the transit gateway, and effectively have communication to all of your different VPCs. It's very common to use a VPN at a remote site or from a user's workstation to be able to gain access to these private VPCs. But there may be times when you want to make your application instances available to anyone on the internet. In that scenario, you might want to use a VPC gateway, or what we refer to as an internet gateway, so that users anywhere in the world will have access to your applications. We might also want to have these devices in each of our VPCs communicate outbound over the internet to other resources. We would use a VPC NAT gateway to provide this communication, and the NAT stands for Network Address Translation. Our VPCs and the private networks that we're running inside of those VPCs can translate to a public IP address to be able to communicate out over the internet. This includes security rules so that your VPCs can connect outbound to internet resources, but you may not necessarily allow inbound access from external devices. And it's not uncommon for many organizations to use multiple cloud providers, but still require connectivity between those cloud providers. We can provide that connectivity through the use of a VPC endpoint, where we create a direct connection from a VPC on one cloud provider to a VPC on another cloud provider. Here's an example that has a number of different VPCs. We've got a virtual private cloud with a public subnet for public applications that people can access from anywhere on the internet. We also have a private subnet on this same cloud provider where we have a private virtual machine. Well, if we have a different storage network, which certainly could be at a different cloud provider, that cloud storage can easily connect to the public subnet over the existing internet and using a VPC internet gateway. But our private subnet is not accessible from the internet, so we need to add a VPC endpoint that will allow our cloud storage to communicate directly to what is a private subnet and virtual machine. Many cloud providers will include additional security that you can layer on top of your VPCs. Security groups and lists are effectively a firewall that's created for your cloud-based services. This allows you to control what traffic can go outbound and inbound to your VPCs. Most of these are based around a series of port numbers and protocols. So you can define a TCP or UDP port number and add that to your inbound or outbound rules in your security groups. You can also add layer 3 addresses to this. So you can add IP addresses that are individual addresses, maybe an entire block of addresses using CIDR block notation, or specify IPv4 or IPv6 ranges directly within your security groups. This is very similar to configuring a traditional firewall, which operates looking at TCP or UDP port numbers. In this example, the inbound rules have a number of predefined rules, but you can customize these as well with your own port numbers specific to your application. In your cloud provider's front end, you would include in your network security list the list of rules that you would like to assign. For example, I have a rule that is inbound using TCP port 443, and any IP address is allowed to communicate inbound with that rule. I have another rule that's an inbound rule for TCP port 22, and it's the same broad range of any IP address. Once you define your network security list, it will be applied to all of your virtual private clouds. And you can see that I have a virtual cloud network for subnet X, subnet Y, and subnet Z. And these very broad network security lists will automatically be assigned to each one of those individual networks. One of the challenges with these network security lists is that they don't provide a lot of granularity. When you configure a network security list, it's automatically assigned to all of your virtual cloud networks, even if you don't need that particular rule in that cloud network, and even if you need additional rules for one of the individual cloud networks. Fortunately, there are ways to add additional granularity using a network security group. With a network security group, I can assign rules to individual virtual network interface cards, or VNICs. So you can see I have similar security rules that I've defined as a network security group. I have network security group A, which is inbound TCP to port 443, and I have a network security group B, which is also an inbound rule to TCP port 22. I've identified these as the network security group A with the green shield and the network security group B with the blue shield. And you can see that I can assign those network security groups to individual network interface cards that may be inside of a virtual cloud network. This one is on a single subnet where I've defined different rules for different interface cards within the same virtual cloud network subnet. You can see by using these network security groups that we do have additional granularity that we could bring down to the individual interfaces. But this also increases the amount of administration required to manage all of these different lists. If you find that you need additional security above this, you might want to look into a virtual firewall or other virtualized platform to include additional security to your application instances. When you're deploying a cloud-based application, you also need to consider who will be accessing that application and from where. If you're creating an application that anyone on the internet would need to access, then you would probably want to include it in a public cloud so that everyone can gain access. But if you're building out a cloud-based application that is for internal use only, you may want to deploy this to your own virtualized local data center where you have a private cloud. In many organizations, we often use both of these, and we need a hybrid configuration of both public and private clouds for all of these applications. One type of cloud model is software as a service, or SaaS. This is commonly associated with software that is on demand. You have a login screen on your browser, you log in, and now you have access to the application. Someone else has written the application, someone else manages the application, your data is stored somewhere within that application, and you don't have to do anything else to be able to use that particular app. You don't have a local installation of software, you don't manage or upgrade any of the software itself. Instead, you simply log in and use the app. This allows for centralized management of the application and the data that you're putting into the application, which means everything is being stored on a third-party cloud platform. This is a complete application offering, and you don't have to do any type of development work to be able to use that app. A good example of software as a service would be an app like Google Mail or Office 365, where you simply log in and use the app. There may be times when you would like to build your own application and deploy and manage your own data, and all you really need are the computing resources to be able to run that application. In that model, you want to use infrastructure as a service, or IaaS. Sometimes you'll see this referred to as hardware as a service, or HAAS, because you're effectively using hardware in the cloud and then using your own software on top of that. This means that you would be responsible for installing your software and managing all of the data associated with that software. If the software needs to be upgraded, you would be the one to upgrade it on your infrastructure as a service model. The application that you're using and the data that you're putting into that application is still in the cloud, but you have much more control over the access and security of that data when you're using infrastructure as a service. A good example of infrastructure as a service is with web service providers, where you can buy time on a particular web server and they make that server available to everyone on the internet. A middle ground between software as a service and infrastructure as a service is platform as a service, or PaaS. This is still in the cloud, but you're the one who manages all of the development efforts to customize the application to your specifications. The cloud provider gives you all of the tools necessary to build this particular app. You can think of this as a series of building blocks provided by the platform as a service infrastructure, and then you build out those blocks to create your own application. The underlying engine that runs the application is the responsibility of the platform as a service provider, and your responsibility is to build and maintain the apps that are running in platform as a service. A good example of a platform as a service infrastructure would be something like Salesforce.com, where they give you all of the tools necessary to create a customized application running on the Salesforce.com platform. Here's an example of a cloud responsibility matrix that you might find with any cloud service provider. In this chart, I've separated out software as a service, platform as a service, infrastructure as a service, and then an on-prem device that you would manage yourself. Obviously, with on-prem, everything from the data to the applications to the physical data center are all the responsibility of the customer. But with infrastructure as a service, you have the physical data center, the physical network, and the physical hosts, all provided by the cloud provider, and then you handle all of the other pieces of that particular application. With Platform as a Service, you can see that network controls, applications, and the identity and directory infrastructure may be shared between the customer and the cloud provider, but you'd still be responsible for the accounts, devices, and the information and data. With Software as a Service, much more of these are provided by the provider themselves. For example, everything associated with the applications is clearly in the responsibility of the provider. Everything above that would still be the responsibility of the customer. So depending on the type of infrastructure you want and the type of responsibility that you're willing to take on, you'll need to pick the right cloud model for your application deployment.